Now we are going to consider the next question, that is this. It's a very important question in which there is a option in which the decarbonylation is mentioned. So what's the meaning of decarbonylation? Decarbonylation is inverse of migratory insertion reaction. It's inverse of migratory insertion reaction, so it's a very important reaction. It means that simply what does this mean? So if I have manganese and we have CO, 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 and we have CH3. So just consider this example, because you should need the short tricks to solve the questions in a very lesser time, because you have to save as much as time you can. So if you have a CH3, it means that CH3 can be replaced on this position, and this position, but it cannot be replaced on the transposition. It can be replaced on this position as well, but on transposition this cannot be replaced. On transposition it cannot be replaced. So what does this mean? This means that CH3 can only be moved to cis position. It means that cis position, it means that CH3 migrates to cis position. So how you are going to solve this? If I am saying that CH3 migrates to cis position, in this what you have to do is we have a CH3, and first of all we have to do decarbonization. So once you have to remove, and after that there is the decarbonization reaction in which CH3 moves to CO, that is the cis CO. Then what you have to do is, if you are doing this particular reaction, you have to do this. So how you are going to proceed? You have to shift the CO. What I am trying to say is that you have this particular CH3 and you have CO. So this CO have to be removed. So in a particular manganese you can get, for example, you have CO30. Here you have CH3. Suppose the CH3 migrates on this direction, and you have CO, you have CO, and you have CO. So this way you are going to get the three products. In this way you are going to get the three products, and in that particular three products, we are getting the percentage, like 25% of this product, 25% and 50% of this. So it's a very short trick. Like if you are going to move your CH3 from one place to another, only in cis position, this and this, not on the trans position, always remember that. Then you are going to get the products in different ratios, 25%, 50%, and again that is 25%. So if I am talking about the 50%, that is the product in which that particular 13CO is trans to CH3. In the C, this is 50%, 13CO is trans to CO. Now for the 25%, 13CO trans to CH3. Okay, so 13CO trans to CH3, just consider this, 13CO trans to CH3, and in 25% no 13CO. So in this there is no 13CO, so that's why we are getting the products in different ratios, 25%, 50% and 25%. So this is the shorter way to solve the question of the decarbonizations. Now this is a very simple question. It just needs 1 minute to solve. In this particular complex, how you're going to solve this? You know that it's a 2 molybdenum atoms, and that is 2x minus 4 is equals to 0. So here x can be positive. It means that the oxidation state of the molybdenum is +2. So we have molybdenum in +2 state. +2, it means that is a D4 electronic system, and we have 2. And we have 2 molybdenum +2, it means we have D4 and we have D4. It means we have total 8 electrons. What does this mean? This means that if you are going to plot the molecular diagram, then what you have to do is you have to say sigma, pi, then we have delta, then we have delta star, then we have pi star, and then we have sigma star. Okay, so this is the molecular orbital diagram. So we have to fill the 80 electrons. So how you're going to fill the 80 electrons? 1 2 3 4 5 6 7 8. So in this particular thing you are going to see, like we have 1 sigma bond, we have 2 pi bond, and we have 1 delta bond. So we have 1 sigma bond, 1 delta bond, and 2 pi bonds. See, we have a sigma bond, we have a pi bond, we have delta bond, then we have pi star, we have delta star, and we have sigma star. So this is the molecular orbital diagram that you have to consider in D4 system. We have D4, so we have 8 electrons in total, and if we have 8 electrons, so we have to fill 1 2 3 4 5 6 7 8. So it means that we have one delta bond, it means that we have two pi bonds, it means that we have one sigma bond. So in this way we have these types of the three bonds. So our answer is, like, we have one sigma bond, we have two pi bonds, and we have one delta bond. So the answer is A. Here our answer is A. So what you have to consider here is, like, you have to approach the questions with very smaller time consuming methods, so that you can get the accurate answer in the lesser time. Now it's a very important question. Like, we have a base first of all, so we have Na positive and H minus. So what it will do, it will usually it will usually abstract the acidic hydrogen. So this is the acidic hydrogen which is nearest to the electron withdrawing group, so you are going to form the negative charge. Okay, so in the first step we get the negative charge here. This negative charge attacks on this, so this is the structure like this: C double bond O. We have OMe on one side, we have OMe on next side. So if we have OMe on left side and we have OMe on right side, what we have to do is, this negative charge ultimately attacks on this position, O negative. So as we have O negative and we have OMe, we have OMe. Okay, so we have this particular group. We have this particular group which attacks. So this particular double bond comes back, this, and the OMe will remove. So in the first step, the minus of OMe happens, one OMe removes and you are getting your product. One OMe removes and here you are getting your product like this, in which you have C double bond O, OM. So this is the A reaction. Basically this A reaction gives us this product. A reaction gives us this product, and in that, this product we are going to add the Br2. In this product we are going to add the Br2. So in this particular Br2 reaction, we are going to get the Br on two sides, one on this side and another on this side. Okay, so in that, this particular reaction, NaO in the presence of MeOH. So this is a reaction in which we are going to proceed via Favor-Escape reactions. So we have a base, we have acidic hydrogen, this. So we have acidic hydrogen. So just consider, this is the acidic hydrogen, this particular base, this is the base NaOM. It means that NaOM, it means Na positive and OMe minus. So this will abstract the hydrogen. There is negative charge attacks on this, Br removes. So we are going to get a cyclic product like this. We are going to get the cyclic product in which we have C double bond O Me. We have C double bond OMe. Here we have Br and a bond like this. Now we have another OMe minus, so we have MeOH as well, we have NaOMe. So in this we have excess of OMe minus. In this particular solvent we have excess of MeO minus. So in this particular MeO minus, it's usually attacks on this particular atom, it attacks on this particular atoms, and the rings open. So if the ring is opening, so if the ring is opening, that means, if the ring is opening, what does this means is, that is, we got the, it means we got the O negative with OMe. We got the O negative with OMe. Okay, so when this will do come back, and this particular bond, this bond shifts on this side basically. So if the bond is shifting, then there is a reaction in which we are going to get the chain will become lesser in number. So the less carbon atoms comes in the chain. Now we have a negative charge, we have C double bond OMe. So why we are getting the negative charge on this end only? Because the negative charge stabilized by electron withdrawing group. Negative charge is stabilized by electron withdrawing group, and here we have C double bond O, and here we have OMe. So this is the reaction. It denotes on this side, Br will remove, and we are going to get the alkene in the product. So if we are going to get the alkene in the product, it means that we have alkene here. We have alkene here this way. So if we have alkene in the product, it means that the alkene should be there on which C double bond or C double bond mu group should be there. So this is the right answer. So on getting the M product, you are getting your answer. So there is no need to proceed to it if you are able to distinguish the products on the first end only. So if you are going to get the M, like what's the M is, so you are going to proceed to the reactions further. So there is no need to solve for the N, but you can check if you know few of the reagent, you can solve the reagent questions very easily in the organic chemistry.